All right, here's some extra tips that just extra little pieces that come up in some Taylor series or some infinite series. One of the things that they like to do is have you rewrite something like x squared e to the 3x. Again, when you look at this, this is a polynomial x squared times an exponential. There's no reason to rewrite x squared as a Taylor series. It already is a polynomial. So let's just leave that x squared there, and then we can write out e to the 3x. Off to the side, you have to think, well, what's e to the x? Well, remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 x to the n over n factorial. The faster you memorize some of these things, the easier these questions will be, because to do e to the 3x, it's just a replacement here. So this is 1 plus 3x plus 3x squared over 2 factorial plus 3x to the third over 3 factorial plus dot 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 3x to the n over n factorial. Lots of times, though, they're going to take this x squared and they're going to throw it in here. Okay? So we're going to simplify this. Let's look at this term, what this is going to be. This is going to be x squared plus 3x cubed. This is going to be a 9. So this is going to be 9 x to the 4th over 2 plus, this is going to get a 3 cubed, and then this is going to be 6. So what's that? 27 over 6 is the same thing as 9 halves? No. Yes, 9 halves. Cool. So it's the same thing, 9 halves, and then that's going to be x to the 5th plus dot dot dot. And then the final term, this is where it gets a little tricky sometimes. They're going to end up rewriting this probably just to confuse you. This term right here, they're going to rewrite as this: 3 to the n x to the n plus 2 over n factorial. They're going to do stuff like that where they're going to take this n and put it 3x to the n is 3 to the n, x to the n, and then x squared times x to the n is what this is, right? This is just 2 extra factors of x, which is sitting right here. And the general term is really important because you want to be able to use the sigma notation, because now this big thing describes this infinite series, which is equal to this. So this thing is straight up equal to x squared e to 3x. And again, they're going to mess with the n's. They're going to throw in pieces here. They can throw them in a geometric sense, right? They can put this as 4x over 1 minus x squared. Well, that's just 4x times 1 plus x squared plus x to the 4th plus 2, and so on. This is just 4x can be factored out. This is 1 over 1 minus x squared. This is just a geometric series with x squared instead of x. And again, you can kind of keep going through those things. So they love to add things in. It doesn't make it any more difficult. There's no reason to include 4x in the expansion. 4x is already a polynomial, so you can set it aside. Okay. One of the other things they're going to do is they're going to mess with the n values. And so let's take a look at something like this. And I want you to think about what you think this is. You have to think hard about this. This is this is an alternating series. Like, I don't know what this is. I can't get an idea of what that looks like. We'll just plug in. When n equals to 0, that's positive, and this is x, so you just get x. When n equals to 1, you're going to get a negative, and when n equals to 1, you're going to get x squared over 2. And then n equals to 3, you're going to get x cubed over 3. And you're like, oh, I get it, I recognize it. This is the natural log of 1 plus x. Look back. This is what this is, and so this series represents the natural log. Now, what if they did this instead? Would you still recognize it as the natural log? Because they might. Something like that. And that's the same thing. Here, you start at n equals to 1, so you start out with x to the first over 1, and you get 1 plus 1, which is 2, 2 makes that positive, and you're like, oh, n equals to 1 gives you the first term. Well, it gives you the exact same series. This is just shifted. This starts at 0 and it starts at n plus 1. This starts at 1 and it starts at n. And again, if you're really questioning whether these two are the same, just plug in the first couple values. Plug in n equals to 1. Positive 1 power over 1 gives you x. Plug in n equals to 2. Odd power, so it's going to be minus x squared over 2. And so on. And you get the exact same thing. So you have to be careful about how they mess around with this. And then one of the last tricks they do is they combine things, or two more things. One, they'll combine things, like let's say we have something like 4x, 2x to the n, or something like this. They will rewrite that as this. Be careful on this. They'll write it like that. They'll take this 4 and realize it's 2 squared. This is 2 to the n plus 2 factors of 2, so it's 2 to the n plus 2, and this is an x and an x to the n, so that's one more factor of x, so it's n plus 1. These are saying the same thing. And both of these are the geometric series 4x over 1 minus 2x, which is crazy. This is a, and this is your r, and so you get this. This is both of these, and again, you could write out their series, but this is the function that's described by this infinite polynomial. Okay? And lastly, they'll do something like this. We'll go n equals to 0. We'll make it alternating, and we will make it x, the 2n plus 2 over 2n plus 1 factorial. Okay, you can pause the video, and I want you to think about what function that is. Okay, anyone know the answer? So, let's think. It's alternating, and I'm dividing by odd factorials. Okay, when am I going to divide by odd factorials? Okay, this kind of gives you a clue that it probably involves a sine function. So somehow the sine's involved. It's an alternating and we're dividing by odd factorials, but look at the numerator. It's x to the 2n plus 2. Well, 2n plus 2 is an even number. Well, what if I ripped off one of those x's? What if I thought of this as x times negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial? Well, then I'd be like, well, this is straight up sine, so then this whole thing must be x sine x. And that's really weird sometimes. You have to look at these two things. The factorial gives you the clue. A sine is always going to be an odd factorial. This 2, we can make that a 1 by just ripping off one of those powers and putting it out in front. And then we have exactly what sine is. Again, you need to memorize that this is sine. It's an alternating, odd-powered factorial, and this x is just fine. We're just out in front. And so those are some of the tricks they're going to do to make things a little more confusing, but hopefully you've seen a couple examples, and now the rest of the things you can, if they're different, you can just problem solve from there. But, you know, messing with the index, messing with the starting point, messing with extra powers of x, you know, those are just little tricks of the trade, because, and eventually, I need to be able to give you this, and you write this, as well as me giving you this, and you tell me that it's exactly equal to this. Okay?